I'll introduce,
Oh, sorry.
go ahead, Ward Howard from the University of Colorado, who's going to talk today about surveying stellar flare rates and properties in new wavelength regime with the galactic bulge time domain survey. Okay? So we'll set the timer up there. The timer's
Perfect.
right there.
I'm really excited to get to talk with you about science for a telescope that hasn't even launched yet. That's a rare opportunity, and I remember when JWST was in this phase and just how exciting that was. So my goal today is to convince you, and perhaps even get you excited about the fact that Roman will enable the first ever stellar flare survey at infrared wavelengths. Infrared flares are poorly understood due to their short timescales and their low fluxes at infrared wavelengths, and also just their random occurrence rate, so it's hard to know when to point a telescope at one to observe it unless you have a large survey. And Roman will obtain imaging in the galactic bulge time domain survey and capture around 400,000 flares. This is an image of the galactic bulge high cadence field specifically. And the color bar here shows the number of flares expected for an average star within our simulations, and I'll go more into that momentarily. And I'll also point out that Roman is the only current or planned facility that's capable of obtaining robust statistics and infrared flare rates as a function of stellar mass and age. I'd also like to highlight that our Cycle 1 program was just funded a few weeks back to enable us to do this science. So I'm excited for that and for our team to get underway. So before I continue, I should answer, what is a solar or stellar flare? Flares occur when magnetic reconnection events in the stellar atmosphere accelerate charged particles down magnetic field lines towards the surface of the star where they heat the plasma. And this results in a light curve profile with a fast rise exponential decay, such as that shown here. And one of the key points of stellar flare science is that stars flare across the electromagnetic spectrum so that no one observation or wavelength really fully captures the physics involved or the energies produced during that stellar flare. You can see this both in this diagram of a stellar flare as well as in this Solar Dynamics Observatory image of a solar flare. And in the diagram on the left, you can see the magnetic reconnection event at the top, where charged particles are then accelerated or precipitated down the magnetic field lines into the footprints of the flare. And the key point is that different physical processes within the flare emit at different wavelengths. And on the right, this is the same solar flare imaged at the same time, and yet it looks very different at different wavelengths, even within a fairly narrow wavelength parameter space. The point of all of this is that we need multi-wavelength observations or observations across the electromagnetic spectrum in order to better understand stellar flares. This is a problem right now for the infrared because the infrared is the least studied regime in statistical flare surveys. So here I've assembled a list of all of the large stellar flare surveys as a function of wavelength, and you can see the IR over here has some catching up to do. The reason the optical is so high is because of the TESS mission primarily. And this raises this question, since flares are fundamentally multi-wavelength events, what physics are we missing out on by not understanding infrared flares? This also has impacts for exoplanets, specifically for transmission spectroscopy at their atmospheres, and this is because stellar signals imprint on the planetary spectrum via something called the transit light source effect. We want to compare a pre-transit spectrum with a transit spectrum to infer what changed, namely the inferred planetary spectrum, which I'm showing here for TRAPPIST-1b, which incidentally is a flat line. That's for another conference. We can talk about that issue later. And in this particular case, there's also something else going on in this observation. I removed it in the earlier plot, but there was the stellar flare that occurred. And so instead of just comparing the pre-transit and the in-transit spectrum, there was a large flare. And this means that these are now contaminated. We don't fully understand how to separate the stellar and the planetary signals. And in fact, this problem can be rather large, with the stellar signals, and especially stellar flare signals, sometimes being an order of magnitude larger than the planetary atmospheric signals we want to look for. What we do know about IR flares, as you may have guessed from the previous slide, mostly comes from JWST. And we've observed now dozens of flares from a handful of stars of different masses and ages. With JWST, ranging from early K dwarfs, I show an example of a flare there on the right, as well as early M dwarfs, all the way up through ultra cool dwarfs such as TRAPPIST-1. And in each of these plots, I show two light curves, one in color and one in gray. The one in color is where I've convolved the JWST spectral time series with the Roman F146 infrared bandpass. And then the one in gray is where I've done the same thing for the NASA test bandpass, which is a red optical band. And the reason I did this is to highlight that there's different physics being probed by the infrared that's not necessarily probed by the optical. And I'd like to dive into that a little bit to explain why I think Roman in particular will be exciting to complement what we've already learned about stellar flares from tests. In other words, if we've done this already for hundreds of thousands of flares with tests, what new thing will we learn from a slightly redder bandpass? When we convolve the JWST time series with both bands, we learn new physics because the infrared actually probes different physical conditions in the star than does the test bandpass. And I'll convince you of that with two correlated plots. The one on the left is a model. The ones on the right are actual data. The model is what's called a contribution function, and it essentially tells you where the emission in a given bandpass comes from. So in this case, for the test bandpass, mostly from atmospheric heights above the photosphere of about 100 to 300 kilometers, and chromospheric temperatures of around 5 to 15,000 Kelvin or so. And then on the other side of the plot with the data, you can see this results in a very rapid, spiky light curve profile at this bluer red optical wavelength, bluer compared to the infrared. When we overlay the F146 bandpass on both of these plots, though, we can immediately see a difference. In terms of the contribution function, it skews towards larger heights above the photosphere. So we're probing a different temperature regime and different plasma conditions. And this is reflected in actual data by a time lag, a later rise towards peak, and a much more gradual decay phase. In addition to specific flares and their properties, we've also learned some things about flare rates from JWST. We've measured flare rates for a handful of stars. Again, TRAPPIST-1, so a late ultra-cool dwarf, all the way through earlier stars such as GJ9827, which is a K dwarf. But the problem is that JWST doesn't observe for very long amounts of time and large numbers of stars. And so what this means is we don't know what typical flare rates are as functions of stellar mass or age, and we don't even know how often the largest flares from the stars that we have measured flare rates for occur. And so there's this large gap in parameter space. And so we need to fill that in. Roman will solve these problems by producing a 1,000-fold improvement in the number of infrared flares. In this figure, I show one of our simulations of a wide field survey observation of a high cadence field in the galactic bulge time domain survey. So this is a 70-day field at 12-minute cadence, and I show a highlight of a smaller cutout to show you what the flare data will look like at that 12-minute cadence. Thankfully, infrared flares evolve more slowly than do optical or UV flares, so the 12-minute cadence is actually perfect for detecting these events. And then we do this, of course, not just for one flare or one star, but for 25 million stars that are detectable with Roman at 12-minute cadence, as well as 400,000 flares within that sample. And that's enough till we can start doing population statistics. So here I've taken our flare yield simulations and I've binned them by stellar mass on the for some reason, here we go. I've binned them by stellar age on the x-axis and stellar mass on the y-axis. And I'll point out that the color bar over here is the logarithm of the number of flare detections, meaning that in many of these bins, we obtain 1,000 or even 10,000 flares, which is enough for robust statistics to understand the flare rates and properties. This actually enables us to complement what we've learned from JWST. This large gap in parameter space over here is actually nicely filled in by Roman. And so to avoid making the plot overly busy, I've only highlighted M-dwarf and K-dwarf FFDs here, or flare frequency distributions, and I've only highlighted them from about 10 million years up to about 1 billion years, but I could have kept going across FGK and parameter space and many more ages. And we'll be able to answer questions such as, are the power laws consistent in energy across all of this region of parameter space, or is there perhaps a broken or log normal power law? We'll be able to test for that at 99.7% confidence by comparing the lower energy and higher energy flares. And this also complements nicely the very small flares that JWST is sensitive to in these time series observations that Roman won't necessarily capture. So I've showed you the results of our yield simulations, but why should you believe me? Where are we getting these yield numbers from? I think it's worth taking a moment and walking through that. So I started by populating the galactic bulge time domain survey footprint using a trilegal-based stellar population synthesis model down to the detection limit, which is about 27th magnitude in F146. And just to give you a feel for how many stars that is, I binned them into 4 different mass regimes here. And then the second step is we want to build a 2D grid of flare frequency distributions or flare rates as functions of stellar mass and age in the IR. So I started with test band rates in the literature and then converted those into the infrared using the 9,000 Kelvin canonical flare blackbody. There's evidence for different temperatures, but it's a good place to start to get a rough approximation of our number of yields. And then once you have that, you can go through each of your simulated sources and you can ask for that specific star. You can interpolate what its expected flare rate is based on its age and based on its stellar mass. And then you can use the signal noise curve for the wide field instrument to determine how many flares you would have expected to detect per day or even per season. And then finally, you can just sum over all of those individual stars to come up with the total flare yield. And so this is what we did. So the flares are there, but how are we going to find them? There's a bit of a needle in a haystack problem with 25 million sources and close to 500,000 flares. As you may have guessed, the answer is machine learning. And so we simulated about 10 to the 4 Roman time series at 70-day sequence, 12-minute cadence, using the Stella pipeline, or so we simulated them and then looked for the flares within those simulated data sets with the Stella pipeline, which is a convolutional neural network flare classifier that was originally designed for tests and has been very effective on that data set. Here's one of my simulated light curves where I drew this from the distribution that I showed you on the previous slide of input stars, and then use that information to simulate realistic astrophysical noise, in this case a young stellar rotator. Then Stella classifies the flares, and you can see the Stella classification probability over here, accurately pulling out our number of flares. And I'll also point out that this worked pretty well, even using model weights that were pre-trained on test flare observations, not even Roman flare observations. And so this tells us that if we were able to do well this way, we'll do even better as we're able to do training sets built on actual Roman data sets with different profiles and systematics. So this actually gave us a lot of confidence that we'll be able to detect stellar flares using convolutional neural networks. And we found true positive, false positive, and false negative, true positive, false negative, and false positive rates of 87%, 13%, and 0.5% respectively, even using these pre-trained weights. And as you might guess, the main dependence here is on the size of the flare that was injected and the stellar magnitude of the source. And so when you get down to the detection threshold, these numbers begin to balloon up, both for the false negative rate here as well as the false positive rate here. And then when you go away from that, they fall off towards 0 very quickly, which is the behavior we want to see. And there are other trends that we found, such as younger, rapidly rotating stars produce higher false positive rates and things I don't have time to go into right now. And so coming full circle, we want to take what we've learned from Roman and then say, how can we propagate this backward to learn more about how the infrared connects to all of the wavelengths that drive atmospheric mass loss or photochemistry? And so standing alone, Roman will make the IR one of the best studied rather than worst studied flare regimes. But we want to know how to connect back into this other wavelength regime, or put another way, where can we get a large sample of simultaneous flare detections? And so for that, I want to introduce you to the Early Evolution Explorer, or EVE. EVE will investigate the early co-evolution of stars and planets with long-term, high-cadence photometry of about 20,000 young stars and nearby clusters obtained simultaneously at near-UV, visible, and near-IR wavelengths. And as one of the EVE science leads, it's my privilege to share that EVE this data set will include simultaneous detections of more than 1,000 large flares in all 3 bands, such as this example simulated detection here. And then we'll be putting this proposal in just a few months to the Small Explorer competition that's ongoing, and hoping for the best. So with that, I will leave up my conclusions, and thank you for your time.
Thank you very much. That's good. Okay, what kind of questions do we have? Okay. Anybody? We'll take the online question now.
All right. Hello, we have a question from online from Hal, who asks, how does one discern the difference between a flare event and a microlensing event in the light curves?
That is a really good question. One of the things I did not go into is that we're actually working on rapid pit filters in order to flag things that are likely microlensing or flare events. And this depends on several factors. One is the wavelength dependence, although we won't get high cadence wavelength information. But the tight one is that flares have a very particular time profile. We've seen this and tested it now in the infrared with JWST with this particular very fast rise exponential decay profile. And in fact, almost all flares are not single events like this, but they're multi-events where you have a very rapid initial peak and then you have a slightly slower secondary peak. And this has to do with the physical structure of the flare on the star. But this is called a peak bump flare. It's something that we found in the literature, and we think we understand why it's happening. So by looking at the substructure in the event, that's one way we can do it. Another is the time scale of the event. Flares tend to vary very rapidly on tens of second time scales, whereas microlensing events are a little bit slower. But there will be some overlap, especially in the low signal to noise regime.
Okay, do we have another question back in the back? Sorry, Ryan, I want to make sure I get back people too.
Hi, Ward. Thank you for a wonderful talk. Could you talk about what the flare stars, what distances they're actually at? Are these literally in the bulge? Are they foreground? Do you worry about extinction, the distances, and your interpretation of sort of when you try to do the statistics on everything? Do you know what I'm getting at?
Yeah, so because I was using a stellar population synthesis model that goes from everything from foreground all the way through the bulge along a given line of sight, it's all of the above. Some sources will be a little bit extincted. Some sources will be less so. Our yields fold that in by including dust and other parameters within the, I would refer you to the Daltio 2022 LSST paper for the way that they built the simulation. I downloaded it off of the data lab and then went from there by extrapolating the data out into the F146 bandpass since it was initially intended for LSST. But we'll have all of the above, and a lot of the flare detections will come from the younger stars. There's actually likely to be contamination from RSCVN flares too. There have been surveys by the drafts team that found that.
Okay, let's give another round of applause for Ward. Thank you. I'll take